In 1991, a single subatomic particle struck Earth's atmosphere carrying the energy of a baseball moving at 100 kilometers an hour. One particle, something smaller than the nucleus of an atom. Physicists named it the "Oh my God" particle because it broke a rule that was supposed to be unbreakable meanness. It exceeded the theoretical maximum energy for anything that could cross deep space and still reach us intact. It should not have been here, and to this day, we don't know where it came from. That mystery traces all the way back to a freezing morning, August 7, 1912. A physicist named Victor Hess was crammed into the wicker gondola of a balloon, more than 5,000 meters over Austria, staring at his radiation detectors in disbelief. They weren't dropping, they were climbing, reading nearly 3 times the ionization he measured at sea level. Something was pouring down from above. Something was out there. And nobody had the faintest idea what. Over the next 10 minutes, we're going to meet every type of cosmic rayness, from the solar particles that reach Earth in minutes to galaxy-crossing giants that shatter our best physics. Let's go. Start with Hess, because everything begins with that balloon. Between 1911 and 1912, he made 7 carefully planned ascents, and the decisive one on August 7th took him to 5,300 meters. The prevailing assumption was that this mysterious radiation came from the ground from radioactive rocks and soil. If that were true, the higher you climbed, the weaker it should get. Hess found the opposite. The radiation intensified with altitude, which meant it was raining down from space itself. But which part of space? The obvious suspect was the sun. Earlier that same year, on April 17th, a near-total solar eclipse gave Hess the perfect test. With the moon blocking the sun's face, the radiation should have dropped. It didn't. It held steady. The sun was not the source. Whatever this was, it came from far beyond our own star. For proving that radiation was genuinely extraterrestrial, Hess would receive the Nobel Prize in Physics in 1936. The name we still use came a decade after that balloon flight. In the 1920s, the physicist Robert Millikan coined the term cosmic ray. He was wrong about what they were. He thought they were gamma rays streaming in from space. Later experiments revealed the truth: these are not rays of light at all. They're charged particles, actual pieces of matter, moving at a hair's breadth below the speed of light. So what exactly is hitting us? Here's the composition, and it surprises almost everyone. Primary cosmic rays, the raw stuff arriving from space before it touches our atmosphere, are about 99% bare atomic nuclei. Stripped naked. No electrons attached. Roughly 90% of them are simple protons, the nuclei of hydrogen atoms. About 9% are alpha particles, the nuclei of helium. And around 1% are heavier elements, everything up the periodic table. Less than 1% are lone electrons, and a tiny trace is genuine antimatter positrons and antiprotons. That's the population. Now let's sort it into types, and I promise you, each one is more extreme than the last. Type 1. Galactic cosmic rays, or GCRs. These are the workhorses, the steady background flux, and most of them come from one of the most violent events in the universe, supernovae. When a massive star explodes, it blasts out a shock wave expanding through space. Particles get caught at that shock front and bounce back and forth across it, and each time they cross, they pick up roughly 1% more energy. Cross it thousands of times, and that adds up into something staggering. This is called first-order Fermi acceleration, or diffusive shock acceleration, and it's essentially a cosmic pinball machine powered by a dying star. In 2013, data from the Fermi Space Telescope confirmed that supernovae really do deliver the necessary punch, miss between 3 times 10 to the 42nd and 3 times 10 to the 43rd joules per explosion. Galactic cosmic rays dominate the sky all the way up to a feature physicists call the NE. Picture the cosmic ray energy spectrum as a line on a graph, sloping downward. The more energetic the particle, the rarer it is. At about 3 times 10 to the 15th electron volts, roughly 3 peta-electron volts, that line suddenly bends steeper. The slope goes from -2.7 to -3.1. That kink is the knee, and it likely marks the ceiling of what a supernova shock can accelerate. Keep climbing in energy and you hit a second bend, the ankle, at around 4 times 10 to the 18th electron volts, where the line straightens out again. That's believed to be the handoff. the point where our own galaxy stops being the source and the particles start arriving from other galaxies entirely. Type 2 brings us much closer to home, solar energetic particles, or SEPs. If galactic cosmic rays are the distant thunder, these are the local storm. They're predominantly protons, mixed with electrons and heavy ions, and they're hurled out by our own sun during solar flares and coronal mass ejections. Their energy runs from tens of thousands of electron volts up to many billions, and here's the frightening part. They're accelerated within just 5 to 10 solar radii of the sun, and they can reach Earth in a matter of minutes. The first hint of them came from a scientist named Scott Forbush, who in February and March of 1942 noticed sudden spikes at ground-level detectors, what we now call ground-level enhancements. But the sun is picky about producing them. Only about 1% of coronal mass ejections generate a strong SEP event. Type 3 is the strangest of the bunch, and even its name admits it: anomalous cosmic rays, ACRs. They were spotted in May through July of 1972 by Garcia Munoz, Mason, and Simpson, who noticed an unusual enhancement in low-energy helium that didn't fit any known category. Their origin story is genuinely weird. Out in interstellar space drift neutral atoms, uncharged, invisible to magnetic fields. Some of them wander into our solar system's bubble, the heliosphere. Sunlight strips an electron away, ionizing them. The solar wind sweeps them up and carries them outward to the very edge of that bubbliness, the termination shock, where they get accelerated to energies of about 5 to 50 million electron volts per nucleon. That termination shock is the same boundary Voyager 1 crossed in 2004, at 94 astronomical units from the Sun. The theoretical mechanism was proposed back in 1974 by Fisk, Kozlowski, and Ramati. And here's the fingerprint that gives them away. Anomalous cosmic rays are mostly only singly ionized pionist. They've lost just one electron pionus, whereas galactic cosmic rays are fully stripped bare. Their composition: hydrogen, helium, nitrogen, oxygen, neon, argon, mirrors the local interstellar medium itself. They're basically samples of the stuff between the stars. Now, Type 4 is the one you should care about personally, because it is happening inside your body right now. When a primary cosmic ray slams into the upper atmosphere, it doesn't just stop. It collides with an oxygen or nitrogen nucleus and shatters, spraying out a cascade of new particles: pions, kaons, muons, electrons, positrons, photons, and neutrinos. This is called an extensive air shower, and the numbers are ridiculous. A single primary proton carrying 1 tera-electron-volt of energy generates about 50 billion secondary particles as it rains down. Most of those die out before reaching the surface, but one kind makes it: the muon. Muons are the dominant cosmic ray particle at sea level, and their survival is a small miracle of physics. A muon at rest lives just 2.2 microseconds before decaying nowhere near long enough to travel the 20 kilometers down from where it's born. By all rights, it should never reach the ground. But muons move so fast, at a mean energy around 4 giga-electron volts, that Einstein's relativity kicks in. Time itself dilates for them. That 2.2 microsecond lifespan stretches out to about 65 microseconds from our point of view, and suddenly there's plenty of time to reach the surface. These particles are living proof of special relativity, falling on your head every second. And I mean that literally. At sea level, roughly 1 muon passes through every square centimeter every minute. About 1 passes through a head-sized volume of space every single second. Right now, as you listen, particles born from an exploding star are threading through your skull. The muons themselves come from even shorter-lived middlemen charged pions, which live just 26 nanoseconds, and charged kaons, which last only 12. Both decay into muons, and pions do most of the work because they're produced far more abundantly. There's one more gift from these air showers. Cosmic rays constantly manufacture carbon-14 in the atmosphere, about 70 tons of it maintained across the globe at any moment. That steady supply is the entire foundation of radiocarbon dating, the method Willard Libby developed to read the age of ancient wood, bone, and cloth. Every archaeological date you've ever heard traces back to particles from space. Which brings us, finally, to the monsters. Type 5. Ultra-high-energy cosmic rays, UHECRs, defined as anything above 1 exa-electron volt 10 to the 18th electron volts. These are almost unimaginably rare and almost unimaginably powerful, and catching them requires the largest detector humanity has ever built. The Pierre Auger Observatory sprawls across 3,000 square kilometers of Mendoza Province, Argentina Minas, roughly the size of Rhode Island Minas, with 1,660 water tanks watching for Cherenkov light, plus 4 fluorescence telescope stations scanning the night sky. After 12 years of data, announced in 2017, Auger tied the highest energy arrivals to sources outside our galaxy, particularly active galactic nuclei, the monstrous feeding black holes at the cores of distant galaxies. But there's a wall these particles are not supposed to cross. In 1966, two teams working independently, Kenneth Greisen at Cornell and Georgy Zatsepin with Vadim Kuzmin in Moscow, reached the same conclusion. A proton with more than about 5 times 10 to the 19th electron volts, traveling more than roughly 160 million light-years, can't survive the trip. It keeps colliding with photons of the cosmic microwave background, the afterglow of the Big Bang, and each collision bleeds off energy through a process called photopion production. This is the GZK limit, a cosmic speed bleed that should cap how energetic any far-traveling particle can be when it reaches us. Nothing should punch through it. And then, something did. October 15th, 1991. The University of Utah's Fly's Eye experiment, out at Dugway Proving Ground. It recorded a particle with an energy of 3.2 times 10 to the 20th electron volts, around 48 to 51 joules, packed into a single subatomic speck. That's the energy of a 140-gram baseball thrown at 28 meters per second, a brisk fastball, concentrated into something smaller than an atom's core. It was moving at 0.9999999999999999957 times the speed of light. When it hit a nitrogen nucleus, the collision energy reached around 2,900 tera-electron volts, about 200 times more powerful than the highest collisions we can produce in the Large Hadron Collider. Its air shower peaked at some 240 billion secondary particles, raining across up to 10 square miles. They named it the Oh My God particle, and it sat far above the Czech wall. It should have been drained below detectability long before arrival, yet there it was, intact. To this day, we don't even know what it was: proton, iron nucleus, or something exotic unknown. For decades, it stood almost alone. Then, on May 27, 2021, the Telescope Array project in Utah caught another one, published in the journal Science in November 2023. Its energy, around 240 exa-electron volts, the researchers compared it to the energy of dropping a brick from waist height, again in one particle. The third most energetic cosmic ray ever recorded. They named it Amaterasu, after the Japanese sun goddess. And here's what makes it worse than the OMG particle. Astronomers traced its arrival direction back Minas, and it points to the local void, a vast empty region of space bordering the Milky Way, where there is simply nothing capable of producing it. The collaboration admitted it may involve, in their words, unknown astronomical phenomena and novel physical origins beyond the standard model. So why should any of this matter to you? Because it already does. The carbon-14 that lets us date the ancient world is forged by these particles overhead. About 1 muon born from a distant catastrophe passes through your head every second of your life. And out there, the OMG and Amaterasu particles hang above a wall our physics says they cannot have crossed, arriving from a void that holds nothing that could have launched them. The universe is running an experiment far beyond anything we can build, firing single particles across billions of light years with energies we can barely comprehend. And every so often, one of them lands here, breaks our rules, and dares us to explain it. So far, we can't. Thanks for watching Cosmic Doodles. Keep looking up.